So up till now we have done question number 13, 14, 15, 16 and question number 11. Okay, so question number 12 is remaining. So after question number 12 we'll straight away jump to question number 7. Okay, so question number 12 is moderately important. Okay, if you don't understand it, don't waste much time on it. Okay, if you understand it, it's well and good. Okay, just revise it. So to understand question number 13 or question number 12, what question number 12 says is that there is a circular ring out here. Okay, but the charge distribution in this circular ring is not uniform. It is given by this relation. Lambda is equals to lambda naught cos phi. What is lambda? Lambda is nothing but the linear charge density. Okay, so if I draw a straight line out here, I'm dividing this ring. I'm dividing this ring into four quadrants. Okay, first quadrant, second quadrant, third quadrant, fourth quadrant. Okay, now at this line or at this point, what is the value of phi? The value of phi is nothing but 0. Okay, so lambda is equals to lambda naught into cos 0. So out here, the value of linear charge density is nothing but lambda naught. Okay, so lambda naught or some positive, very high positive constant. Okay, now as I increase the value of phi, what will happen? As I increase the value of phi, what will happen? The value of cos phi decreases. So if the value of cos phi decreases, what will happen? The value of lambda will also decrease. So out here, the value of this charge or the magnitude of this charge is decreasing as we go up. Now at 90-degree angle out here, this point in the ring, phi will be equals to 90, no? Phi will be equals to 90. Okay, so what is the value of cos phi? The value of cos 90 is nothing but 0. So out here would have 0 charge or 0 charge density multiplied by dx amount of length is equals to 0 charge. Now what happens to cos in second quadrant or what happens to cos in this quadrant? It turns to negative, no? So cos 90 plus something is negative. Okay, so in this quadrant or the second quadrant, the cos will be negative. So out here, what will happen? The cos will change its value to negative. It will keep on increasing as I go towards cos 180. Okay, so the value of lambda will be maximum at cos 180. Okay, it will be minus lambda naught out here. See, out here the value of lambda is lambda naught. Out here the value of lambda is minus lambda naught. Understood? So the linear charge density is negative. The charges out here will also be negative. Now what happens to cos at third quadrant? It remains negative. So out here, as I go from 180 to 270, the charge will slowly decrease. Okay, slowly decrease, and it will become 0 out here. Now in fourth quadrant, okay, what happens to cos? Cos becomes positive, no? So after this 0, cos will again become positive and reach out to maximum value at this one. Understood? So this is our charge distribution out here. Okay, this entire thing is our charge distribution out here. Okay. Now I need to find out the electric field at the center of the ring. Electric field at this point at the center of the ring due to the entire ring. Okay, so how do we approach that? Before finding out electric field to the center of the ring, let us divide this ring into two parts. Okay, two halves. The positive half and the negative half. Okay, and the reason behind doing this is the concept of integration. Okay, so if you integrate this entire thing over the entire length, what will happen is the problem doesn't take into action the means the integration will come as sine phi. Okay, and when you integrate sine phi from 0 to 2 pi, what will happen is the net electric field will come to be as 0, which should be wrong in the question. Okay, see, the mathematical approach, physics is nothing but careful application of mathematics. Okay, that's the only part of physics, no? So instead of integrating the whole thing in a linear way, what we'll do is divide this ring into two parts. Okay. Now if you observe the right hand part, the net electric field would be in this side direction. Acha. due to positive charges. If you observe the left hand part, okay, the net electric field would also be in this direction. Okay, the electric field due to positive charges and the electric field due to negative charges, okay, will be equal in magnitude. Understood this much? And the part that I was trying to explain is, if you integrate, I'll just tell you at the end of this question, okay, what would be the problem if I don't divide this entire thing into half part. So first let's solve by this method, then I'll tell you the problem that I'm encountering if I don't divide this ring into half. Okay, understood? And if you observe carefully out here, due to symmetry, the vertical component of this ring, or the vertical component of electric field, would be zero. Why? See, the vertical component of electric field generated by this much element would be cancelled by the vertical component generated by this much element. Similarly, the vertical component generated by this much element will cancel out the vertical component generated by this much element. Understood? So the vertical component of electric field would get cancelled out here. Understood this much? So out here, if I just erase these two and write down total electric field, total electric field is nothing but electric field due to positive charges plus electric field due to negative charges. Now what do? I take an element out here of phi, okay, and this length d phi, and this angle d phi. How much is this much length? Elemental length dl. What is the value of this dl? The value of this dl is nothing but r into d phi. So r into d phi. Okay. Now what is the elemental charge out here, or dq? So the elemental charge dq is nothing but linear charge density into length. So what is the linear charge density? Lambda into length is nothing but r d phi. The value of lambda is not constant. The value of lambda is given by this function. Okay, so dq would be given by lambda naught cos phi, which is the value of linear charge density, into r d phi. So you got the value of dq. Problem is, what is the electric field at this point due to this much part of the wire? The electric field at this point would be this, in this direction, isn't it? Okay, so the electric field, or DE, let's not write E, let's write elemental electric field, is nothing but K dq by r square. Understood? So the elemental electric field due to this much length, okay, at the center, is nothing but K dq, or K into charge out here divided by r square. Understood? But charge out here is nothing but charge density into this much length, but this much length is nothing but r d phi. Fair and fine. Now d is the total electric field due to this much element. No, what do we need to do? We only need to find out the horizontal component of this electric field. Why? Because this horizontal component and this horizontal component will be added. Okay, so if I draw a line out here, if this angle is phi, okay, this angle is also phi, isn't it? So d cos phi, or x component, or horizontal component is equals to de cos phi. Okay, or is equals to, what is the value of d? K dq by r square. K, what is the value of dq? The value of dq is nothing but lambda naught cos phi r d phi. Lambda naught cos phi r d phi. Okay, divided by r square, into cos phi, Okay, so let's simplify this one. Or E horizontal, is equals to, see, out here r and r square will get cancelled out. Okay, r and r square is getting cancelled out. Cos and cos becomes this cos and this cos becomes cos square phi, cos square phi. Okay, so our integration becomes k lambda naught in by r into cos square phi d phi. Out here, let's take k lambda naught by r outside. Okay, let's take k lambda naught by r outside the integral. Understood? Or EH is equals to, or horizontal component of electric field is equals to k lambda naught by r integration of cos square phi d phi. Now my second part of the questions. What are the limits to this integral? What are the limits to this integral? See, at 0, it is positive, no? What I'm trying to do out here? I'm trying to find out the electric field due to this entire positive charge, okay? And separately finding out the electric field due to this entire negative charge, okay? So for this entire positive charge, the phi would start out here. The phi out here is nothing but minus pi by 2, minus pi by 2, okay, or minus 90 degree or plus 270 degree. Both will have the same value or both will have the same effect, okay, to the value of positive 90 or to the value of plus pi by 2 or to the value of this pi by 2. Understood? So I'm integrating from here to here to find out the electric field due to this positive part of the thing. Okay, so we come to the next page. To integrate this one, okay, to integrate the horizontal component of electric field at the center due to this portion of the ring, you need to integrate this one. Now to integrate this one, you need to learn two mathematical concepts. Okay, so let me give you them. Cos square phi into d phi is nothing but phi by 2 into sine 2 phi by 4. But sine square phi d phi is nothing but phi by 2 minus sine 2 phi by 4. So these are the two mathematical concepts you need to know to solve this problem. Okay, and this is basically taught in your elementary integration. Not elementary integration, it is taught in class 12 in the chapter of integration. Here basically what you have to do is convert this cos square phi in terms of 2 phi. Okay, so cos theta plus theta is nothing but cos square theta minus 1 or 2 cos square theta minus 1. Then you have to integrate those terms. Understood? So basically I won't be divulging into the integration of this part. Okay, this will be taught in integration. Okay, what I'm interested is about out here. So the horizontal component of magnetic electric field due to the semicircular ring is k lambda by r into theta by 2 plus sine 2 theta by 4. Okay, the limits of integration are minus pi by 2 to pi by 2. Now just solve this limit. Okay, pi by 2, pi by 2 divided by 2 if I take the upper limit. Okay, plus sine 2 into pi by 2 is nothing but pi divided by 4. This is the first. Minus pi by 2 divided by 2 plus sine minus pi by 2 is nothing but minus pi divided by 4. Okay, I'm just solving for this much part. See, sine pi is nothing but 0 and sine of minus pi is also nothing but 0. Okay, sine pi by 2, this becomes pi by 4. This entire term becomes pi by 4. This entire term becomes pi by 4. Okay, so pi by 4 minus pi by 4. Okay, out here I have done a mistake. It should be minus out here, no? There is a minus missing out here. Why? Minus pi by 2 divided by 2, isn't it? Okay, I have taken minus pi by 2 out here. As out here also I should take minus, no? So pi by 4, this minus and this minus becomes plus. So this entire term becomes is equals to pi by 4 plus pi by 4, which is equals to pi by 2. Okay, is equals to pi by 2. So horizontal component of electric field due to this much length of wire is nothing but k lambda naught by r into pi by 2. Okay, now if I see this much part of the wire, see, due to symmetry, okay, the horizontal component of electric field due to this much part of the wire will be same as magnitude of the horizontal component of electric due to this much part of the wire. Okay, this part or the positive part is pushing it towards left and the negative part is pushing it or pulling it towards left. So total electric field at the center would be how much? 2 into k lambda naught by r into pi by 2. 2 and 2 will get cancelled, so it would be pi into k lambda naught by r. So that is the total electric field towards the left, or that is the total electric field due to the entire ring. Understood? Okay. So now I'll go through some common misconception. The first misconception: why didn't I integrate the whole thing together? Okay. See, if you integrate the whole thing together, what will happen is electric field is nothing but k lambda. Lambda is nothing but lambda naught cos phi into this elemental length r d phi. Okay, r d phi. This is the dq charge divided by r square, isn't it? K lambda dr is nothing but dq divided by r square. And to integrate this from 0 to 2 pi. What happens when you do this is nothing but, see, electric field is nothing but k lambda naught by r. Okay, this r and this r square will, okay, k lambda naught by r into cos phi d phi. Okay, so from 0 to 2 pi. Now the interesting property of cos is nothing but cos graph looks something like this. Okay, from 0 to 2 pi. Understood? So the, if you integrate from 0 to 2 pi, no, what will happen is the integration will give out the term as 0, or this positive area would cancel out the negative area. But out here what is happening is electric field due to these positive charges is not cancelling out the electric field due to these negative charges, isn't it? They are being added. See, due to these positive charges, electric field is in this direction. Due to these negative charges, the electric field is in this direction. So both the electric field will get added. Understood? That's why I did not integrate the entire thing at one go. I divided the ring into two parts. Okay. If I integrated it by this method, the mathematics would say that the electric field due to this component is getting cancelled by the electric field due to this component. But in physics, that is not happening practically, no? That is not the thing that is happening out here. Understood? So that's why I divided the ring into half. Now the second misconception, not misconception, it's more of a curiosity. Okay, how did I derive those formulas of integration? See, how did I derive this formula? Okay, see, these are basically topics of mathematics. Then also I'll just show you in brief. Okay, the remaining portion just ask your mathematics teacher. So out here, if I say cos 2 theta is nothing but cos square theta minus sin square theta. Okay, or 2 cos square theta minus 1. This is nothing but the value of cos 2 theta. Okay, or fair and fine, or cos 2 theta minus 1 or plus 1 is equals to 2 cos square theta. Okay, or cos 2 theta divided by 2 plus 1 divided by 2 is equals to cos square theta. If I substitute this value out here, what do I get? Or integration of half plus cos 2 theta divided by 2 into d theta. And when you integrate this one, you get somewhat like theta by 2. Okay, for cos you get plus sine 2 theta by 4. Okay, For sine square theta d theta, just ask your mathematics teacher. It will follow the same method. Okay. Now the second part of the question. Okay. If the initially the ring was in this plane, okay, the ring is being tilted in this plane after. So this plane I'm drawing it as something like this. Okay. Like this. The ring is in Z plane. Okay. Now due to this Z plane, okay, the maximum positive charge is out here and the maximum negative charge is out here. The positive charge will slowly decrease out here and the negative charge will slowly increase. Out here what will happen? The negative charge will slowly decrease and the positive charge would slowly increase. The second part of the question is asking at this point, at point X, from the center of the ring, find out the electric field at this point. Okay, understood? So I'm just rotating this ring little bit upward. So the entire ring, okay, the entire ring was in this plane. I'm just rotating it such that the positive charges, okay, the maximum of positive charge comes out here, the maximum of negative charge comes out here. This entire ring is rotated by 90 degree. Okay, this entire ring is rotated by 90 degree. So out here positive charge would keep on decreasing, negative charge would keep on increasing, negative charge would keep on decreasing, positive charge would keep on increasing. And you have to find out the net electric field at this point. Okay, at X from the center of the ring. Okay, fair and fine. Now if you observe the symmetry, or if you observe the symmetry of this ring, the positive part of the ring, okay, will have horizontal component and vertical component in downward direction. So horizontal component would be in this and the vertical component would be in this direction. This ring or this positive ring is trying to push it down and right hand side. The negative component of the ring will try to pull it. The vertical component of the negative component would be in this direction and in this direction, isn't it? This direction. Okay, this direction. This is the negative component, this direction. Now if you see carefully, the magnitude of this one will be equal to the magnitude of this one, or the magnitude of the horizontal component of electric field due to the upper part of the ring would be equal to the horizontal component of electric field due to the lower part of the ring. So the magnitude of this value would be equal to the magnitude of this value and they would cancel out each other, no? The only part would be remaining is the vertical component, isn't it? So whenever you are left with complex electrostatic geometry, before trying to solve the question, try to figure out the geometry. Okay, how the things are getting cancelled or which portion are in symmetry. Before solving the question, always try to figure out the symmetry of the geometry. So your most of the question will be solved. Well, not most, nearly 99% of the question will be solved if you figure out the geometry of the question or if you find out the symmetry of the question. Understood? So out here, both the electric field due to the positive charge and the electric field due to negative charge would get added. So if I take an element out here, dx, okay, dx is nothing but r d phi or r, acha, d phi out here is nothing but this much angle, okay, and this angle has nothing to do with this angle. Let this angle be omega or okay, sigma, okay. So this angle theta has nothing to do with this angle sigma, okay. So let me take dx element or dx length out here, dx length of this elemental strip. So this elemental strip has charge dq, isn't it? And what is the electric field out here, or what is the vertical component of electric field due to this dq? The vertical component of electric field, see, due to this elemental charge, the electrical field would be in this direction, no? D, okay. and this angle would also be phi, sorry, sigma. So the vertical component would be dE sine sigma. So vertical component of electric field, E vertical, due to positive charge, would be equals to dE sine sigma. Now what is the value of dE? The value of dE is nothing but k dq by the distance between them. No, what is the distance between them? The distance between them is nothing but r square plus x square under root. So r square plus x square under root, okay, into sine phi. Fair and fine. Now what is the value of dq? The value of dq is nothing but lambda into dx, okay. So the value of dq is nothing but lambda. Lambda is nothing but lambda naught cos phi, and dx is nothing but r d phi, okay, divided by under root of r square plus x square, acha, whole square. Out here it should be whole square into sine phi. Now see, this is kept constant. You know why? Because doesn't matter wherever in the ring you are, this length is never going to change. This length is going to remain constant. Okay, doesn't matter where, in which portion of the ring you are, this length will remain constant throughout the ring for this axial portion. What will change is I have to integrate this charge for the total ring out here. Okay, so first I'll integrate the positive portion of the charge. Okay, so the positive portion, see, if I integrate the total charge, you know what will happen is the positive would cancel out the negative and the total charge would come out to be as 0. So I'm avoiding to do that. Okay, what I'll try to do is I'll integrate the first half, then I'll do the second half. Okay, so electric field due to the vertical component, or vertical component of electric field due to positive charges, is nothing but this much charge. So what is the value of sine phi? The sine phi will also remain constant. Doesn't matter wherever in the ring you are. Okay, this angle phi will always remain constant. So sine phi is nothing but perpendicular by hypotenuse, or perpendicular is nothing but r divided by hypotenuse under root of r square plus x square. So if I write vertical component of electric field due to positive charges is nothing but k lambda naught. Let's take the constant term outside. K lambda naught r into r square divided by r square plus x square to the power 3 by 2. If I combine these two terms, it becomes r square plus x square to the power 3 by 2. Okay, and what are the variable terms? Cos phi d phi. So cos phi d phi. Now what are the limits of integration? See, out here it was 0, no? Cos phi out here it was 0. So it was being rotated by 90 degree. So out here cos phi is equals to 0. So out here minus pi by 2 to pi by 2, or 270 to 0, whichever you are comfortable with. Okay, sorry, 270 to 270 to 90. Okay, this is 270, this is 90, or minus 90 to plus 90. So minus pi by 2 to pi by 2, or vertical component of electric field is nothing but k lambda naught r square by r square plus x square to the power 3 by 2. What is the integration of cos phi? Nothing but sine phi. Okay, the limits of integration are minus pi by 2 to pi by 2. So this becomes nothing but 2. If I put the limits out here, this entire limit will become 2. So vertical component of electric field due to positive charge is nothing but 2k lambda naught r square by r square plus x square to the power 3 by 2. Okay, now this vertical component of electric field is only due to this positive charge, you know. For the negative charge will have the same magnitude as this positive charge. So total electric field is equals to vertical component of electric field due to positive charge plus vertical component of electric field due to negative charge, which is equals to twice of vertical component of electric field into positive charge, because both of them has the same magnitude due to symmetry. Understood? So E total should be equals to 2 into 2k lambda naught r square divided by r square plus x square to the power 3 by 2. Okay, 2 and 2 will get multiplied to become 4, and out here E total would go out here. Okay, the total electric field at a point in axis would be given by this formula. Okay, if you have understood this one, it's well and good. Okay, if you haven't understood, you can still somehow skip this one. Okay, you can skip this part of the problem if it is difficult for you, if it is that much difficult for you. Okay, so what I'll do out here is I'll recap some portion of the theory so that you don't get confused in the upcoming portion. Okay, so the important thing that I'm going to discuss out here is for spheres, okay, inside electrostatics. Basically, spheres are nothing but divided into hollow spheres, which is also known as shell, and solid sphere. That means the entire sphere is filled with something. Okay. Okay. In hollow sphere, whenever I'm giving any charge, the entire charge gets distributed on the surface of the shell, because the charge has nowhere to go. Okay. But in case of solid sphere, what happens is if it is non-conducting, okay, the charge will get distributed inside the volume. But if the sphere is conducting, that means if the sphere is made up of conducting material means silver, gold, or any conductor, what will happen? Even if the entire sphere is filled with mass, the charges will get deposited at the surface of the sphere. Understood? So even if this sphere is completely filled, suppose a completely steel sphere, okay, it is not hollow inside, is given some charge, all the charges will get deposited at the surface of the sphere. Understood? So basically a conducting solid sphere behaves as a hollow shell for a for the chapter of electrostatics. Okay, only in non-conducting sphere will the charge get distributed inside the volume of the sphere. Understood this concept? Okay. Now see this question. Okay, a sphere of radius r carries a surface charge density sigma is equals to ar, where a is a constant vector and r is the radius vector of a point sphere relative to its center. Find the electric field strength vector at the center of the sphere. Okay, so what the question is asking is out here, charge density is given by sigma is equals to a into r. So in this pair, what is happening is charges are distributed out here. Okay, in this pair. Now, due to the distribution of these charges, I have to find out the electric field at the center of the sphere. Okay. Now, the first question should be how are the charges distributed? Okay. So, what kind of sphere is it? Is it insulating sphere or non-conducting sphere or conducting sphere? See, I don't care about it. Okay, it can be either a shell or a conducting sphere. But the charge are distributed at the surface. And how do I know? Surface charge density is given in the question. See, surface charge density is given in the question. That means what? The charges are distributed at the surface, isn't it? So out here, sigma is equals to A into R. But A is a vector quantity and R is a vector quantity. Okay, you can draw any position of the A vector as long as A vector connects to the center of the sphere. Okay, so let this be A vector and let our radius vector be R. Okay, let this be the R vector. Let this R vector be R out here. Now, what is the difference between if I draw the R vector out here and if I draw the R vector out here? Okay, see, A dot R is nothing but, if you see out here, surface charge density is A dot R is nothing but magnitude of A vector into magnitude of R vector into cos theta. But theta is the angle between a vector and r vector. So what is happening out here is, as the value of theta is 0, so the value of cos 0 is nothing but 1. So at the top of the sphere, what will happen? Maximum charge concentration will be there. That means the charge density is maximum at the top. Now, as I increase the value of theta, what will happen is the value of cos theta will decrease. So as the value of cos theta decreases, the surface charge density decreases. So as I decrease or as I increase the value of theta, the charge density slowly decreases. Okay. And what happens when theta is equals to 90? What happens when theta is equals to 90? The surface charge density becomes 0, isn't it? Now see, this is not a circle. This is a sphere. Okay. So you have to take an elemental ring out here. Understood? So if I look from the top, okay, if I look from the top of this sphere, if I look from the top of this sphere, what happens? At theta is equals to 0, we have a maximum charge concentration or maximum surface charge density. As I increase the value of theta to some value out here, we'll have little bit of lesser charge density. Okay, as I'm increasing the value of theta, my charge density is getting reduced and reduced. Okay, out here very little charge density, and at theta is equals to 90, our charge density will be 0. So at theta is equals to 90, what happens? Our charge density becomes 0. Understood? So similar kind of thing will happen out here. My charge density is getting reduced and reduced, isn't it? Now theta is equals to 90, my charge density will become 0. And as I cross theta is equals to 90, what will happen? The value of sigma will get negative. That means after 90, what will happen? The charges will change its polarity. That means after 90, the charges will become negative. Okay, and as I'm increasing the value from 90 to 180, the magnitude of negative charge keeps on increasing, and this will happen till theta is equals to 180, where we have maximum concentration of negative charge. So similar kind of thing will happen out here, because this is a sphere, isn't it? So from 0 to 90 degree we have positive charges, and from 90 to 180 degree we have negative charges. Understood? And we have to find out the electric field at the center of the sphere due to this charge distribution. Okay, now my strategy for this question would be, I would cut the sphere into half. Okay, then find out the electric field due to these positive charges. The electric field due to the center due to these positive charges will be equals to the electric field due to these negative charges at the center. See, the positive charges will push it downward and the negative charges will pull it downward. So if I multiply the electric field due to positive charges by 2, I'll get the total electric field. The problem is, how do I find out the electric field due to positive charges? Okay, so what I'll do out here is, I'll take an element out here. Okay, this is nothing but elemental ring out here. So this elemental ring out here, fair and fine. Out here, this angle is nothing but d theta. So from here, r, and this angle is nothing but d theta. Okay, this is nothing but a vector. Now sigma is equals to ar cos theta. What is the charge in this much portion of the ring? Okay, the charge in this much portion of the ring will be how much? Sigma into dA, where dA is nothing but area of the ring. Okay, now charge, I have to find out the electric field due to this ring on the center. Okay, so if I integrate this ring from 0 to 90, okay, I'll get the electric field to this entire hemisphere, isn't it? I have to integrate this ring, from theta is equals to 0, that means top of the ring, to theta is equals to 90. So I'll get the electric field to this entire hemisphere, isn't it? So just let me delete this one and these diagrams also. Okay, so electric field is nothing but, or electric field due to a ring is nothing but k q x by r square plus x square to the power 3 by 2. You must remember this formula. Electric field due to a ring is nothing but kq, or charge on the ring, into x, axial distance, divided by radius of the ring square plus axial distance square to the power 3 by 2. All of you have remembered this formula, or most of you have learned this formula, isn't it? Now the problem is out here. Q is what? Q is nothing but elemental charge on this ring, no? So elemental charge is nothing but Q, or Q. Okay, how much is Q out here? Sigma, or charge density, into elemental area. But elemental area is nothing but the area of this circular ring. Understood? Okay. Problem is, sigma I know is given as A R cos theta. What is the value of elemental area of the ring? Elemental area of the ring is nothing but perimeter of this ring into this much length. How much is this much length? If I see this ring was made from circular hemisphere, no? So this much length is nothing but R into d theta, isn't it? So this much length would be nothing but R into d theta. But area of the ring would be 2 pi into radius of this ring. What is the radius of this ring? R sine theta. See, if this is the radius, this much distance would be R sine theta, is nothing but this much distance, and this much distance is nothing but R cos theta. Okay, so 2 pi r, or 2 pi r sine theta, 2 pi r sine theta, which is the perimeter of this ring, into length. Length is nothing but r d theta, r d theta, which is nothing but the elemental area of this ring. Now if I integrate all the charges, or if I take all the values, a, okay, r, r and r becomes r cube, 2 pi, okay, into sine theta cos theta d theta, to sine theta cos theta d theta. This is nothing but the value of q out here. Understood? The value of x, or axial distance from the ring, the value of x is nothing but r cos theta out here. So the value of x is equals to r cos theta, and the value of r, which is nothing but the radius of the ring, the radius of the ring is nothing but r sine theta. So out here r is equals to r sine theta. Now if you substitute all these three in this formula, or electric field into a ring, okay, what will I get? E is equals to k. The value of q is a r cube 2 pi sine theta cos theta d theta, into x. The value of x is nothing but r cos theta, divided by r square, or r sine theta. Okay, this r is nothing but the radius of the ring, and this r is nothing but the radius of the sphere. Okay, so r sine theta whole square plus x. The value of x is nothing but r cos theta whole square to the power 3 by 2. Okay, now see, this r sine theta will become r square sine square theta, and this r cos theta will become r square cos theta. Okay, if I take r square common, it will be r square into sine square theta plus cos square theta. So if I take r square common out here, it would be r square into sine square theta plus cos square theta. And what is sine square theta plus cos square theta? 1. So the entire denominator would be r square. Now this r square into 3 by 2 is nothing but r cube. R square into 3 by 2 is nothing but r cube. So the entire denominator would be r cube. This r cube and this r cube would get cancelled. Okay, so we are left with electric field due to this ring is nothing but k a 2 pi sine theta sine theta. This cos theta and this cos theta would become cos square theta into d theta. And out here there is one more r out here, no? So let me write this one more r out here. Understood? And the limits of this integral, what are the limits of this integral? From theta is equals to 0, okay, so that means from the top of the hemisphere to theta is equals to 90. So this entire circular ring at theta is equals to 90 from 0 to pi by 2. Okay, from 0 on top of the hemisphere to pi by 2. That means the last ring is at sine 90. Understood? Now all I have to do is I have to integrate this from 0 to 90. Okay. Now I have solved the entire integration on the right hand side. Okay. It is nothing but integration by substitution, where you have to take t is as cos theta. Okay. And you will integrate to form, the answer will come out to be as 1 by 3. So this will be taught in your mathematics. Okay. I'm not wasting my time out here. This entire term will come out to be as 1 by 3 for the limits of 0 to pi by 2, isn't it? So the net electric field would be RKA 2 pi by 3 into 1 by 3. And this electric field was due to half of a sphere, no? So the total electric field would be how much? Electric field due to the positive part and electric field due to the negative part, which will be 2 into RKA 2 pi by 3, or is equals to 4 RKA pi by 3. Understood? See, I'm multiplied by 2 because due to symmetry, the electric field due to the positive charge will be downward, and the electric field due to the negative charge will also be downward, no? The positive charge is pushing it down and the negative charge is pulling it down. And due to the symmetry of charges, the magnitude of electric field due to the positive charge would be equal to the magnitude of electric field due to the negative charge. So this was our question out here. Okay. So this question is very much similar to the previous question. Okay. In the previous question was what? There was a charge distribution given by sigma is equals to a dot r, or a r cos theta. Okay, a dot r, and the charges were maximum at the poles, minimum at the equator. And as I go through the poles to the equator, the magnitude of the charge reduces, isn't it? Out here, out here, out here. And the electric field at the center due to this charge distribution was given by how much? E was equals to, or electric field at the center was equals to 4 R K A into pi by 3, isn't it? 4 R K A into pi by 3. Okay. Now if I just rearrange this for our convenience, okay, I'll just rearrange this as 4 pi by 3 K into AR. 4 pi by 3 K into AR. So 4 pi by 3 K into AR, isn't it? And what was the value of AR? The value of AR was nothing but sigma. Okay, so this can be written as E is equals to, or electric field at the center due to spherical charge distribution is nothing but 4 pi by 3 into K sigma. Understood? In this question, however, the difference in this question is, instead of giving surface charge density, volumetric charge density is given. See out here. Okay, volumetric charge density, isn't it? Volumetric charge density. Okay, so the charges are distributed throughout the volume of this sphere. That means out here it will have the same charge distribution, but similarly, as I reduce the radius vector, that means as I go towards the center, the magnitude of charge decreases. Okay, and same thing happens with all the side charges. Okay, all the side charges also behave in the same. Okay, as I'm going towards the center, the magnitude of this charge will decrease. As I go towards the center, the magnitude of this charge will decrease. It will happen throughout the sphere. Now I need to find out the electric field due to this entire charge distribution. Understood? So what is the similarity between previous question and this question? Can I say in this question, volumetric charge density is equals given by A dot R. So same type of function is given, or AR cos theta. Okay. Now, what is the relation between sigma and rho? Okay, and how do we solve this kind of question? See, if I just take an elemental shell out here, elemental shell, okay, of thickness dr. The elemental shell has radius r and thickness dr. And what is the electric field due to this elemental shell at the center? The electric field due to this elemental shell at the center will be given by this formula, where sigma is nothing but the charge distribution. Understood? We'll have the same formula. Okay. Now, if I integrate this equation from 0 to r, we'll get the electric field due to the whole span. No? So electric field is equals to 4 by 3 pi 4 pi by 3 k into sigma. But we have a problem out here. Okay, I cannot use sigma. I have to use rho out here. So what is the relation between rho and sigma? See properly out here. See, we integrated this shell by introducing dq. No, dq was nothing but the charge content inside this shell, or charge content in the shell. So dq is equals to sigma into dA in the previous question. Sigma into dA, or charge density or surface charge density into elemental area. In this question, however, dq, or the charge content in this exact same shell, would be nothing but volumetric charge density into dV, or volumetric charge density into the volume of this much thin shell. Understood? In the previous question, the elemental charge in this shell, okay, the elemental charge was equals to sigma into dA, or surface charge density into elemental surface. In this question, however, it will be volumetric charge density into volume of this shell. Okay. Now, what is the volume of this shell? The volume of this shell is nothing but area of the shell, or surface area of the shell, into dr. So volume of the shell is nothing but surface area of the shell into dr. Now, if I take both of this equation, okay, down here, and equate it, sigma into dA is equals to rho into dA into dr. dA and dA would get cancelled. So rho is equals to sigma by, or sigma is equals to rho into dr, or sigma is equals to rho into dr. So the same formula, when I use out here, what will get converted? This sigma will be equals to rho into dr, no? Rho into dr, isn't it? So electric field due to this elemental shell out here would be nothing but 4 by 3 pi k into, what is the value of rho? The value of rho is nothing but ar into dr. And I have to integrate this r dr from 0 to r for the entire sphere. This entire sphere is filled out here. This entire sphere out here is filled with charges. Understood? Okay. Some of you might have questions, sir, why didn't you take cos theta out here? We already took the cos theta. Okay, if you go into the entire details of integration, no, out here dq is equals to cos theta, you have to integrate that one, and ultimately we'll come to this equation again. Okay, I'm just applying some shortcut out here. Okay, nothing more, nothing less. Now the question becomes simple. Or electric field is equals to 4 by 3 pi k a into r square by 2. The limits of integration are from 0 to r. Or electric field due to the field square 4 pi k a into r square by 2. Out here 2 and 2 will get cancelled. So electric field is equals to 2 by 3 pi k a r square. Isn't it? So the question was simple enough if you have just studied the previous question. Understood? Okay. So in order to do the next question, we'll learn a little bit about something called flux. Okay. Flux. Whenever you hear flux in your syllabus, flux is nothing but dot product of field and area. Flux is nothing but dot product of field and area. Now, in your entire syllabus, there are two kinds of flux. One is electric flux, and the second one is magnetic flux. Magnetic flux. Okay, electric flux given by sigma is nothing but dot product of electric field and area. Similarly, magnetic flux given by phi b is nothing but dot product of magnetic field and area. Okay, now where are electric flux used? Electric flux is used in Gauss law. Gauss law. Okay, where electric flux is equals to dot product of electric field into area, which is equals to total charge inside divided by epsilon naught. Where else is it used? In case of displacement current. Okay, remember the chapter of electromagnetic waves. Displacement current is equals to epsilon naught rate of change of electric flux with respect to electric time, or rate of change of electric flux with respect to time. And where is magnetic flux used? In your syllabus, magnetic flux is primarily used in electromagnetic induction. Okay, or how change in magnetic field through area produces current in the area. So Faraday's law, where EMF or potential difference or EMF is equals to minus d phi b by dt, isn't it? EMF is equals to minus d phi b by dt. So whenever you hear the word flux, flux is nothing but dot product of field and area. In your syllabus, you'll learn flux two times. First one is electric flux, okay? The second one is magnetic flux. In electric flux, we'll learn Gauss law and displacement current. Displacement current is from the chapter of electromagnetic wave. Displacement current from the chapter of electromagnetic wave. Okay, and in the chapter of electrostatics, we'll learn Gauss law. Similarly, magnetic flux we'll learn in the chapter of electromagnetic induction, Faraday's law, Lenz's law. Lenz's law is basically just about direction. We'll learn about Faraday's law. Now the problem is, primarily in class 11, you will have been taught area is a scalar quantity, but I have taken area as a vector quantity out here. So how do I take area as a vector quantity out here? Okay, so I'll little bit give you a brief methods of taking area as a vector quantity. Methods of taking area as a vector quantity, as a vector quantity. Okay, the first rule is area vector is always perpendicular to the surface. Okay, area vector is always perpendicular to the surface. What do I mean is that, suppose this is the area, or suppose this is a plane. Okay, the area of this paper is somewhat, say, 10 square centimeter, not 10 square centimeter, it will be much more than 50 square centimeter. Okay, now if I want to take this 50 square centimeter area as a vector quantity, what I must do? Area vector should always be pointing in this direction or perpendicular to the plane of paper. Understood? So area vector is always perpendicular to the plane of paper. Now one more question might come on. Which perpendicular? The top perpendicular or the bottom perpendicular? Both are perpendicular, no? Out here this area vector is also perpendicular. Out here this area vector is also perpendicular. Both are equally correct. Okay, you can take both. Now the second type of question is, if there is a curved surface. Okay, suppose there is a curved surface. How do I take the area vector out here? Isn't it? So for curved surface, what do we do? Suppose this was a curved surface. Okay, what you do is you take the elemental area dA in this direction and you integrate all the elemental area in their various direction. The elemental area of this area would be integrated in this direction. The elemental area of the second area would be integrated out here. So similarly, you have to integrate all this elemental area, and all this elemental area would be perpendicular to the plane. Understood? So this is the method in which you take uh, the elemental area for a curved surface. Now the third type of question. Okay, what happens for a closed surface? Okay, suppose a cube is there. Okay, how do you take an elemental area for a cube or a closed surface? When a closed surface has an area, no? So basically, for a closed surface, the area vectors is always pointed outside the surface. For closed surface, for closed surface, area vector is always pointed, is always pointed outward. Understood? That means the top area vector would be outward. Okay, this side area vector would be towards right. It cannot be towards left. This side area vector would be towards this direction. Understood? This area vector would be bottom. So for a closed surface, the area vector should always be pointing outward the surface or outside from the surface. This much you have understood. Okay. After this, what I'll do is I'll take few examples of flux. Okay. I'll just show you few examples how flux are calculated. So flux is nothing. Whenever I say flux is nothing but dot product of field and area, isn't it? So the first example I'm taking is, suppose there is a electric field out here. Okay, E. And there is a plane of paper out here. Okay, the electric field is in this direction. Okay, this direction. The plane of paper is in this direction. The area of the plane of paper is nothing but A. What is the flux out here? Flux is nothing but E into A. Now the second example. Okay, the same electric field of magnitude E, the same paper of area A. But instead of keeping the paper, I have kept the paper in slanting direction. Okay, slanting direction, such that the area vector, see, the area vector out here is what? Parallel to E. Okay, the area vector out here makes an angle theta with the electric field vector. This is area vector, this is electric field vector. This is area vector, this is electric field vector. So what will be the flux in the second case? Flux out here is nothing but E into A into cos theta, where theta is the angle between electric field vector and area vector. Understood? So the importance of dot product of field and area is nothing but in cos theta. So if I keep the plane of paper, suppose the electric field is in this direction, plane of paper or area vector is also in this direction. That means what? Out here on the left hand side, cos theta becomes 0, or cos 0 is nothing but 1. Okay, whereas on the right hand side there is an angle between area vector and electric field vector. Understood this much? What happens if I keep my electric field out here? This is the electric field and my paper is in this plane. What is the angle between area vector and electric field vector? 90. And what is the value of cos 90? 0. So the flux out here would be nothing but 0, isn't it? Not E dot A, it would be 0. So you can also assume as, or you can also imagine flux as number of field lines passing through the area. Okay, you can also imagine a trick out here. Okay, flux can be imagined as number of field lines passing through the area. passing through the area. Passing through the area. Fair and fine. Now, how do I take flux for a closed surface? Okay. So suppose a cube is given, and that is kept in a uniform electric field. Okay. It is kept in a uniform electric field. What is the total flux of this cube? Or what is the total flux to this cube? Okay. See, this cube will have six surfaces, top surface and bottom surface. This is surface one. This side surface or left surface and right surface, isn't it? And the third one is back surface and front surface. Understood? All will have electric field. See out here. The angle area vector out here. The angle between area vector and electric field vector in the first case is 90. So flux out here would be equals to 0. Flux due to the top surface and the bottom surface of the cube would be 0 because the angle between area vector and the electric field vector is 90. Similarly, for the back and front surface, flux would also be 0. Out here also flux is equals to 0 because the angle between area vector and electric field vector is 90. Okay. For this surface out here, area is in this direction, area vector is in this direction. For this surface, area vector is in this direction. Note out here, the area of the or the magnitude of area of the right hand side is equals to the magnitude of area of left hand side. So on the left and right hand part, flux is equals to, see, on the left hand part, okay, the angle between area vector and the electric field vector is 180 degree. Understood? And cos of 180 is -1. Okay. So out here, flux is equals to E into A into -1 or minus A. And due to right hand side, okay, or due to right face, the angle between area vector and electric field vector is how much? 0 degree. So cos 0 is nothing but 1. So plus EA. So the total flux through both the surface would be equals to 0. But the flux through individual surface is not equals to 0. Understood? So the total flux through this entire cube is nothing but 0 plus 0 plus 0 is equals to 0. Understood? So these are few examples of flux that I have given you that will be useful, and you have already learned these all things. Okay. So let's proceed to the next question, which contains a question of flux. Okay. In this question, a very long rod is out there. Okay. A infinitely long rod is out there. Fair and fine. This long rod has a linear charge density lambda. And there is a circular disc out here. This is not a circular ring. This is a circular disc. We have to find out the total electric flux through this circular disc, okay, due to this charge carrying rod or charge carrying infinite rod. Understood? Now, what is the formula for flux? Flux is nothing but E dot dA, isn't it? Or dot product of electric field and area is nothing but electric flux out here. Okay. So if you remember, okay, what was the electric field due to a semi-infinite wire? If I take an ring out here, this is the entire thing is nothing but a disc out here. This entire thing is disc out here. Okay. And disc is made up of elemental rings integrated over 0 to R. So in this entire disc, what did I do? This entire disc, what did I do? I took an elemental ring of thickness dr. Okay, dr thickness. And if I integrate this ring, elemental ring, from 0 to R, I'll get this disc. Okay. Now my question is, what is the flux? Listen to my question, okay. What is the flux due to this charge carrying infinite wire on this elemental ring? Understood? So on this elemental ring, first you have to find out what is the electric field. The electric field in y direction would be k lambda by r, and electric field in x direction would also be k lambda by r, k lambda by r. Now if you see this properly, E dot dA is nothing but dot product of electric field and area vector, no? So the area vector of this elemental ring would be downward, isn't it? So the angle between Ex and downward area vector would be 90. So no component or this component of electric field wouldn't provide any flux out here. Understood? All the flux would be provided by the Y component of electric field due to this semi-infinite wire. So my question is, electric flux is nothing but what is the value of electric field? K lambda by r, k lambda by r. And what is the elemental area, or what is the elemental area of the ring? The elemental area of the ring is nothing but 2 pi r into dr, isn't it? So this is the flux. Now if I integrate this entire thing, I have to integrate this entire thing from 0 to capital R. So if I integrate this entire thing from 0 to capital R, I'll get the flux throughout the entire circular disc. Okay, so out here R and R got cancelled. So flux through the entire disk is equals to 2 pi k lambda into dr from 0 to r, or flux is equals to 2 pi k lambda r. Simple enough.